This conference will now be recorded.
So, hi students, today hereafter what we'll do, we'll take up special topics from both 11 and 12 chapters, and we'll try to understand that particular topic in detail with all possible physics in it, because these special topics are such an important topic that in every exam at least one question will be there from that particular portion or particular topic. So therefore better to understand such topics in deep and try to solve as many as possible different problems on that particular topic. So I have thought that hereafter we'll take up various topics from 11th and 12th chapters, and we'll learn that particular topic in detail, in and out, and we'll take up all the concepts which are relevant for NEET exam, JEE exam, etc., and all other competitive exam. Okay, so that we can easily solve any problem from this kind of topics. So such a special topic here we have taken up today is the projectile motion. This comes under motion in 2D or motion in a plane. So therefore we can say that projectile motion is a special case of two-dimensional motion. And how do we define projectile? What is a projectile? Projectile is a particle which can move in or which moves in vertical motion. So projectile is a particle which moves in a vertical plane with some initial velocity, but its acceleration is always free fall acceleration, which is acceleration due to gravity g, and that will act downward direction. Such a particle is called projectile because it is projected or it is launched, and its motion is called projectile motion. So therefore projectile motion is a special case of two-dimensional motion. So you might be thinking, what is this projectile motion? From this definition it is not very clear, right? So you might be thinking whether we have any real life example. Answer is yes. In our day-to-day life we experience this kind of motion. So I'm just trying to indicate some of those real life example, like say this is a basketball playing. When you go to the playground, and or you can watch in the TV that how the motion of the basketball is. See, this is happening in a plane. So the basketball is moving in a plane. Okay, and you can look here very nicely that the ball is moving. See, it is moving vertical direction as well as in the horizontal direction, vertical direction as well as horizontal direction, and that's how at some point it goes and it goes to the net. Okay, so this is how projectile moves in two dimensions. Okay, and this is one of the real life example, and most of them are in play itself. We can understand. See, we have another very famous example of playing a football when a suppose Messi is taking a kick, free kick, okay? So that time how the ball moves is analyzed by this projectile motion. So this is some kind of projectile motion. Similarly, for cricket ball also, when suppose when Dhoni hits six, so the motion of the ball, cricket ball, is projectile motion. Similarly, throwing a javelin. So throwing a javelin is also a projectile motion, right? So javelin goes like this, and it hits the ground. All right. So recently in 2021, Mr. Neeraj from Indian Army, I guess, he had won the Olympic 2021 and won the gold medal for India in javelin playing, right? All right. So similarly, so these are from play. See, one very important and very interesting example of projectile motion is the motion of the relief item when it is thrown from helicopter. Suppose there is a flood or any other natural disaster, when the army persons try to help the victims from helicopter, they throw medicines and any other relief items from the helicopter, and see, they have to actually properly analyze the motion of that relief item and aim at the target people, okay, so that they can give them, like, give the relief item to the proper person. So this, the motion of this projectile is then very, very important, and we can see it has application in our real life, okay. So this can be even thought of like in the war field, when the fighter jet launch the missiles to the enemy bankers, etc. So then also the motion of that missile is some kind of projectile motion, okay. So projectile motion means it is projected or launched, okay. So what are the aims here, or what are the contents in this particular lecture? What we are going to ultimately learn in this projectile motion? Actually, we will be analyzing the projectile motion. See, as I was explaining here, we need to give the relief item to the proper person. So we need to know where horizontally how much it should go, and vertically where it should land. So those kind of things we need to analyze, isn't it? So therefore, we need to analyze the motion of a projectile. How do we analyze? Actually, we will be analyzing the projectile motion using the tools of two-dimensional motion. In fact, the kinematic equation we have learned in motion in a plane, kinematic, kinematic equations. Okay, so these tools will be using tools for two-dimensional motion. So these tools are actually kinematic equations. Okay, kinematic equations, or kinematics, we can say kinematic equations, or simply kinematics in two dimension. So here, to analyze the projectile motion, we need to define and understand and derive three parameters which are related to the projectile motion. One is time of flight. We'll discuss when we go to this time of flight. We'll discuss in detail what is this, and so I'm just mentioning what are the things we are going to learn here. So time of flight, then maximum height that can be attained by a projectile, and horizontal range of a projectile. So these are three important parameters which we need to learn, and we need to learn how to derive it, and sometimes we need to remember the final formula, because you will be given some information and asked to find out maximum height attained by a particular projectile. Okay, so equation of path of a projectile. See, as I showed you here, this is the path of a projectile when you throw from helicopter. So this is the path. We need to know the path because we are going to use this projectile motion in our day-to-day life. Even in case of basketball also, we have shown you the projectile. Sorry, path of the projectile or the trajectory of the projectile. So this is the line of sight from the helicopter, but trajectory of the projectile is this. Okay, so we'll be learning equation of path of a projectile or trajectory of a projectile. Trajectory. Okay, all right. Now we'll understand some of the important concepts, relevant concepts in projectile motion, some general information. See, the projectile motion here, while discussing projectile motion, we are neglecting the air resistance all the way. Okay, so look here, this figure. When a particle is launched or projected with certain initial velocity, so it will start moving with initial velocity and making an angle. See, this initial velocity is v0 here. This is the velocity vector v0, and it makes an angle theta 0 with the horizontal. I say that is x-axis, horizontal axis, and y is the vertical axis. So the velocity of the particle which has been given from here, from this origin, is v0, making an angle theta 0 with the horizontal. Then see, when it makes an angle, see, I'll write this figure a little bit, looks like hazy. I'm just writing here. Look, if this is a particle which is velocity making an angle theta 0 here, this has velocity v0, suppose. So obviously, which makes an angle theta 0 with the horizontal, it would have two components of velocity. One is v0 cos of theta along I cap direction, and another one obviously will be v0 sine theta 0. This is theta 0 along j cap direction. So I can say the velocity vector, initial velocity vector, this is v0x I cap plus v0y j cap. Okay, v0x, this particular thing is, see, v0 cos of theta 0 I cap, and v0y is v0 sine theta 0, that is along j cap direction. Okay, so we can see that projectile has two components of velocity. That means there will be motion in two directions. So that's why we are saying this is a special case of two-dimensional motion. And we'll look few more important points here. So Galileo first mentioned Galileo first mentioned that projectile motion projectile motion or two-dimensional motion which has horizontal and vertical motion, and this kind of motion can be actually considered as two simultaneously occurring independent one-dimensional motion. So projectile motion is actually considered as separate or independent, I should say independent, two independent simultaneously occurring one-dimensional motions. Okay, two motions are happening. One is along the horizontal direction along x-axis, another one is along the vertical axis. So projectile motion is considered as combination of two independent simultaneously occurring one-dimensional motion. And here air resistance has been neglected, as I mentioned. And as I have shown you here, velocity vector has two components, one along x direction, another along vertical or y direction. And you can see here will be, see, initial velocity has been given to the particle, but no force has been given to the particle, right? So there will be no acceleration along the horizontal direction. Okay, so the velocity in the horizontal direction is constant of motion. Okay, constant velocity is constant, so the motion, horizontal motion, is constant of motion for this particular projectile. Okay, not only this particular, any projectile, that horizontal motion is constant of. But obviously we'll see in case of inclined plane, horizontal motion also will be accelerated motion, not uniform or not constant of motion. Then vertical motion is under gravity, as I have mentioned in the definition itself. Vertical motion is under gravity. That means gravitational acceleration will be always acting downward, that we have already learned. And in the vertical direction, since it is going opposite to the gravity, the velocity vector in the vertical direction, velocity vector will be gradually decreasing, as you see here. See, the vertical component is this much, horizontal component is this much, and this remains constant throughout. Okay, but vertical component, see, goes on decreasing. See, this is the magnitude of the vertical component, and here the magnitude of the vertical component is 0. That means velocity gradually decreases as the projectile moves upwards, and at the maximum height, the particle has zero vertical velocity, and thereafter, see, this is the maximum point. Okay, maximum value, here it attains to the maximum height, and where the vertical velocity is 0, but anyway it is under gravity, right? So as it passes the maximum point here, it gains vertical velocity again in the opposite direction. See, it was moving in the upward direction. Now if I draw a point over here, so vertical velocity gradually rising up due to gravity. There will be again a vertical velocity, but at the same time you can see the magnitude of the horizontal velocity remains constant all the way. So when we project a particle, suppose we throw a stone in the vertical direction making an angle theta, but obviously it comes to the ground again, but not at the same point from where it was projected. See, when it lands to the ground again, it doesn't land at the same point because it has two motions. One is along the horizontal direction, another one along the vertical direction. So the point where it uh, lands is this point. Okay, this is the landing point over here. And when it lands here, you know, the velocity vector, total velocity vector, has the magnitude same as the velocity, magnitude of the velocity which was there in the beginning. Okay, this is very surprising that the velocity remains the constant. Velocity remains the constant when it reaches to the ground. Okay, or the total velocity remains the same. Magnitude of the total velocity vector remains the same, whereas the direction has become opposite to the direction of this. Suppose here the velocity vector v0 is 2i cap plus 3j cap at this point, and where it lands, the velocity, same velocity vector, magnitude of the velocity vector will be the same, but with a negative sign in the vertical velocity component, because horizontal component doesn't change. So 2i minus 3j. So this is the velocity vector after landing, and the magnitude of the velocity while landing will be same as the velocity, magnitude of the velocity which was given in the beginning or initial velocity. Okay, this we should write as final velocity. All right, so with this we'll just go to the next place. Now we have already discussed two independent and simultaneously occurring one-dimensional motion in projectile motion. So now we'll see one by one what are the independent two different component of one-dimensional motion. So first is horizontal motion. So projectile has horizontal motion as well as vertical motion, and this horizontal motion, you can see the particle velocity number one, point number one, velocity is uniform or constant. And what is that velocity? And that velocity is v0x, that is v0 cos of theta. Okay, this is along x direction or horizontal. All right, and with time this is not changing, right? Because there is no acceleration. Okay, no acceleration. Therefore, at any time, and at any position, the velocity of the projectile in horizontal direction, or I should write along horizontal direction, is V0 cos theta itself. V0 cos theta. So V0 cos of theta. Here theta is theta 0 in fact, so we'll write theta 0 itself. So what will be the displacement then? Displacement, horizontal displacement at any time. So horizontal displacement at any time will be suppose d is equal to V0 cos of theta 0 if that time is at any time t, so that t is actually V0 cos of theta into t. This will be the displacement. Okay, so we have got few points here. That the velocity remains constant or uniform velocity and there is no acceleration. Okay, and it has got the displacement at any instant of time t is v0 cos theta 0 into t, because this is uniform velocity. V0 t is equal to, or uniform velocity into time is actually displacement of the particle, projectile. Okay, we'll go to the vertical motion. So in this case, look, the velocity, initial velocity of the projectile v0y will be equal to v0y will be v0 cos sine of theta 0. Okay, this is sine of theta 0, v0 sine of theta 0. Okay, now look here, this motion, vertical motion, is under gravity. Vertical motion is under gravity. Vertical motion is under gravity, and so the acceleration in this case will be minus g. Okay, in the vertical direction. So velocity at any instant of time, velocity at any instant of time will be velocity at any instant of time will be how much? See, we know v is equal to final velocity is equal to initial velocity plus acceleration into t. So that formula of kinematics we will be using here. So v0 y t at any time t will be given by v0 y minus of g into t. Okay, this is the velocity at any time. Okay, then what will be the displacement in this case? Displacement at any instant of time, displacement at any instant of time at any instant of time any instant of time t is given by, see, we know displacement will be s is equal to ut plus or minus half at square, right? In this case a is minus g. Okay, a is minus g, and Putting that here, we'll get some s, let us say, that is the vertical displacement in the vertical direction will be written as u0 yt minus half g t square. Okay, v0 y t is v0 sine of theta 0 into t minus half g t square. Okay, so this is actually velocity, sorry, displacement at any instant of time, and I have given the velocity here at any instant of time t. Okay, now you might be thinking, then what is the net motion? See, what will be the net motion then? Net motion. See, net velocity will be velocity vector. This will be velocity vector y j cap. Okay, and if you want to find out velocity at any instant of time, what will be the velocity? Magnitude of the velocity, at least. Magnitude of the velocity at any instant of time t will be obtained from this v0x whole square plus v0y. So this will be the magnitude of velocity vector at any instant of time. Okay, in this case, velocity, initial velocity in this figure is given as u. We can just go with this. It's also for the derivation case, because v0, this suffix and all, it will be a little bit complicated. So u, suppose, is the initial velocity, making angle theta. Okay, so at any instant of time, velocity will be given by this vector. Okay, and this is the formula. And now see, if we want to find out what is the angle the velocity vector makes with the horizontal at this particular position, how to find out? In fact, what is the angle here? This velocity vector makes with the horizontal. So that can be a question. So in this case, we know this is a vector, velocity vector, and there are two components. Okay, this ux is nothing but u cos of theta, and this is u sine theta. Okay, now how do we find out the angle that the velocity vector makes? So that is theta is equal to tan inverse v naught y by v naught x. Okay, or in other words, this is the vertical velocity, this is initial horizontal velocity. So vy by vx. Okay, this is the angle. Here in this particular figure, it is v sine theta. Okay, so this this is, let us keep this as vy, and this is vx. Okay, so we have now discussed few important and basic points of projectile motion. Now look, we'll go to little deeper subject. At any instant of time, this actually, let me write once again, this theta will be actually given by tan inverse Vy. That means, you have got V0 y minus gt at any instant of time. What is the angle? So this will be tan inverse this is V0 x cos of theta. Okay, and this will be, in fact, this I'll write a little bit again in another V0 sine theta 0. Okay, so this is the thing. You can in fact write it some other format also. This can be written as V0 tan theta 0 and this gt by cos theta. Anyway, so this is fine. Now we'll see what will be the change in the linear momentum. What will be change in the linear momentum? And so velocity and change in the linear momentum we will find out now. See, initial velocity we have already found out. Velocity okay. Now final velocity we have found out. Let us write this as final, and this initial let it be this, or okay, let me write this in terms of, let me write in in terms of this figure itself. Okay, so initial velocity vi is equal to u if I write in terms of vector. U x plus I cap, sorry, I cap u y j cap. So that means, u cos of theta I cap plus u sin theta j cap. Okay, and what is the final velocity? Final velocity vf, say u cos of theta as it is I cap minus j u sin theta. Now what is the change in the velocity? Total change in the velocity? So total change in the velocity will be delta u it will be final minus initial if we take the modulus of this final minus initial, see this will cancel each other, this will be okay u, so this will be 2u sin theta. Now total change in the momentum, how it will be? Total change in the momentum, total change in the linear momentum so that is m into delta u, so m into 2m into u sin theta. Okay, this is the total change in the linear momentum in case of projectile motion. Now we will see the important parameters of the projectile which we need to know for understanding the details of the motion of a projectile. So as usual, I have taken y-axis along the vertical direction and x-axis along the horizontal direction. And suppose a particle or a projectile has been given a velocity u along, okay, making an angle theta with the horizontal. Okay. Now, as I showed you that the particle actually will attain a maximum in the vertical direction, and then it will be coming down to the ground again. This is the point where it coming down. Okay, so in this case you look one thing, for the time being you just learn that the path of the projectile will be parabolic and very much symmetric like this, very much symmetric. That means the total velocity vector of the particle here, and if you draw a line over here and this point, so total velocity vector here and total velocity vector here will be the same. Okay, will be the same. So that's how it is symmetric, very symmetric. Now what I'm trying to say is that the particle, see, since the particle is moving under gravity or against the gravity, the vertical component of the velocity, that is u sin theta, that gets reduced due to acceleration due to gravity, that is g. And since the velocity is lost by the particle, the particle will actually the particle will move in the vertical direction with decreasing velocity, and at the maximum height its total vertical velocity becomes 0 and the whole velocity will be becoming horizontal velocity. Okay, so there are three terms basically, or parameters. One is time of flight, as you see in the figure, time of flight, and another one is actually horizontal range, which is denoted by r. time of flight is denoted by t, and maximum height is denoted by h. So what is this time of flight? Actually, as I said, the particle or the projectile obviously will come to the ground and it lands after some time. Okay, as soon as you throw it upward, even if you throw over your head vertically, directly vertically upward direction, then it may come onto your head itself. But if you make an angle theta with horizontal, then the particle velocity, particle projectile trajectory will be a parabola, and it lands somewhere else. So the total time it takes from launching to land, okay, this duration of total duration of time, okay, or duration of this time of flight is actually duration of the duration of the flight in the air, in air. Okay, that is actually time of flight. So in between what happens, the particle goes up, losing velocity gradually, and become rest here in the vertical direction. So velocity is vy is 0 here, or yeah, so velocity in the vertical direction will be 0 for the time being. It will come to the rest, and then just after that point, maximum point, it starts moving in the vertically downward direction along with increasing velocity. Okay, so how to find out the time of flight? See, first of all, it has initial velocity in the vertical direction, that is u sine theta. Okay, you know the acceleration minus g, and it is moving. Okay, so moving up to the maximum height, that means final velocity here vy will be 0. So I can use this formula that final velocity vf is equal to initial velocity u I minus at. A is the acceleration in the vertical direction, minus a, here it is g actually. So initial velocity of the particle in the vertical direction minus gt, this will be the final velocity. But at the maximum height, when it reaches at maximum height, so this I can give a time. Suppose this time is t1 or okay, t. So this t, this is 0, this is vi is actually u cos theta here, and this a is minus g here. Okay, or a minus is given already, so I'll take plus g and t. So this time, see, this time can be written as u cos of theta by g. U cos of theta by g, this is the time it takes up to here. Okay, and since the motion of the projectile is symmetric, then it takes the same time to come down. So here, while going up to maximum height, it takes time. T is equal to u cos theta by g, and while coming down, it takes the same time, that is u cos of theta by g. Why is this true? Oh, I'm sorry, this is not u cos theta, this is u sine theta. U sine theta in the vertical direction, u sine theta by g. This is u sine theta. Here also it will be sine theta. So what is the total duration of the flight? Total duration of the flight, or it is called time of flight, which is written as capital T, that is 2 into this time. Okay, the time it takes to go to the maximum height and the time it takes to come down to the ground from the maximum point, okay, or maximum height. So 2 into u sine theta by g. All right, so this is the time of flight. Okay, so time of flight, I'll write just the formula here. So time of flight, we got 2u sine theta by g. So you might be thinking, why to do this much? This much, we can just directly find out what is the total time it takes. Oh no, I think this is the best way to do the calculation of time of flight. We have already covered. Now what we'll do, we'll find out what is the maximum height. So now it is actually, we can use two things. One is the time we have obtained u sine theta by g. You can use that, or you can, and you can just find out s is equal to half ut minus half a t square. That this formula we can use, or else, see, we have got initial velocity u sine theta along this u cos theta, and see at this maximum height, and this maximum height is noted by capital H. So we have to find out this maximum height or the maximum displacement here. So here the velocity will be 0. Initial velocity we know, and acceleration due to gravity is the acceleration. So now if we use the third equation of kinematics of v square is equal to u square minus 2gh. So if we, this is final velocity, this is initial velocity. Okay, so if we use this formula, see where the final velocity here is actually 0 at the maximum point, and initial velocity is given u sine theta. Okay, then I can write h is equal to u sine theta whole square divided by g. Okay, divided by g. So what is the maximum height? How do you find out maximum height? The maximum height is then given by h is equal to u square, that means this, into sine square theta divided by 2g. This is the maximum height attained by the projectile, right? Now we have found out two parameters: time of flight, that is 2u sine theta by g, and another parameter, that is the maximum height. Okay, now we'll see what is the horizontal range. So this is called horizontal range. Okay, horizontal range. What is that horizontal range? The horizontal range is the horizontal distance between the initial point and the final point where the projectile lands. Okay, initial position from where the launching or projection of the particle happens, okay, and where it lands. This is the final point, initial point and final point. So the linear distance, or the distance between the initial and final point, is called range. So how to find out range? This is nothing but horizontal displacement, right? The maximum horizontal displacement, or horizontal displacement, horizontal displacement, displacement. So how to find out displacement in the horizontal direction? We have already seen that. See, in the horizontal direction, I say the total, we know the total duration of time, or the time of flight, we know that. Okay, time of flight we know, 2u sin theta by g. We know that in the horizontal direction, the velocity of the projectile is uniform or constant. So this r, horizontal range, will be velocity along the horizontal direction into the time of flight. So u cos of theta, if this is theta, this is u, so this side it will be u sin theta. So u cos theta, this is the velocity in the horizontal direction into the time t, that is the time of flight. So we get 2u cos of theta into t is this much. Okay, now see 2 cos of theta into sine of theta, and this is u square. So you know this will be u square sine 2 theta by g. This is the maximum, sorry, this is the horizontal range. Now this, you can see here, this horizontal range depends on the angle of projection. Not only that, it depends on the initial velocity as well. So if suppose you have been asked to find out the maximum horizontal range for a given velocity, okay, maximum horizontal range, then this range will be maximum. See, this will be maximum when the sine theta range will be maximum, r goes to r max, if the sine 2 theta is 1. This factor becomes 1. This will give you the maximum horizontal range. And when is it possible? 2 theta is equal to 90 degree or theta is equal to 45 degree. So this is the condition for maximum horizontal range, which I have written here maybe. So condition for maximum horizontal range, I write here condition for maximum horizontal range. So what is that? See, r max is equal to u square sine 2 theta. This has to be 90 degree by g. I think yes, it is g. Okay, so u square by g, this will be the maximum r max. Okay, and what is the condition? Theta has to be 45 degree. Condition, this is the condition, theta has to be 45 degree. At 45 degree, the horizontal range will be maximum. All right, now look, I have written here, I have shown you here some figures. You can be very much surprised to see that for the given velocity, for a given velocity, I think yes, I'll just be here. For a given velocity, value of, okay, for given value of velocity, any projectile can achieve or cover same range horizontal range at two different projection, different angles of projection, angles of projection, that is, one is, if one is theta, then the other one is 90 minus theta. For these two angle, for the given velocity u, there will be two different angle of projection for which the horizontal range will be the same. Look, I'll take up any angle, suppose 15 degree, theta is 15 degree, so 90 minus theta will be how much? 90 minus theta will be 75 degree. Look this figure, this is for 75 degree, this is for 15, so same horizontal range. Now look with 60. So if the 60, theta is 60, then another angle is 30. So 30 and 60, this is the curve for 30, this is the curve for 60. Look these two guys, I'll just remove the other one. Let us cover 2. So this is for 60 and this is for 30. So they are also having the same horizontal range. Similarly for 45, see 45 is the only angle for which the range will be the maximum. See this one. Okay, this is the curve for 45. All right, so this is how for two angles of projection for the same horizontal range we could see here for the same horizontal velocity, obviously for same horizontal velocity, same initial velocity. Okay, now we'll see the path of the projectile. So what is the path of the projectile? How do you find out path of the projectile? First of all, this figure you look, I have taken u is the velocity vector, so it has got two components as usual, u cos theta along the horizontal direction and u sin theta in the vertical direction. So I'm just considering after time t, the projectile, I'll finish with this for today's class. Projectile reaches at P. So at this position, what are the x and y coordinate? X coordinate, anyway, it will be as usual, displacement along the horizontal direction, u cos of theta into t. So from here, can we find out what is t? T will be x by u cos theta, right? Let us keep this. Now, what is y? Y, you know this, y will be u y t minus half gt squared. What is uy? Uy is u sine theta. I'll put it here. U sine theta. What is t? T is x by u cos theta. See, I'm putting from here. And half gt squared. T is again x by u cos of theta whole square. So look here, what we get, x tan theta minus half, or I write in this way, minus gx square in the numerator divided by 2u square cos square theta. Cos square theta. Okay. So you can see that this is this equation is very much similar to y is equal to ax plus bx square, which is which is an equation of a parabola. So this is anyway theta is constant, means it doesn't vary. Okay, it doesn't vary. So this is a constant. I can take this as a x, and this g minus 2 g divided by 2 y square cos square theta along with minus sign, I can take that as b. Then it is actually resembling this equation resembles this particular equation, which is equation of a parabola. Equation of a parabola. That's why the trajectory is a parabola. Trajectory is a parabola. Okay. All right. So I'll stop it here with this. I'll just give you a brief overview of what we are going to discuss in the next class. So next class we'll discuss various examples numerical examples. Okay, various numerical examples. We'll discuss various numerical examples. Oh, I'm sorry. Examples. See, in the examples, what we will be discussing. See, sometime projectile will be thrown from vertical. Sorry, from some, suppose from some height or from the top of the building horizontally with given certain velocity, which will reach, and at any instant of time what will be the velocity, etc. we'll be discussing. Okay, in this case we'll analyze the motion, what will be the range, what will be the time of flight, etc. Similarly, when from any height it is thrown making an angle theta with the horizontal, what will be the trajectory and what will be the range, etc. we'll be discussing. And at the same time we will be discussing what happens if a person who is in the see, if the projectile is thrown from an inclined plane which has made an angle alpha the horizontal, so then if that is thrown, okay, what will be the range, all the things we'll be discussing in case of inclined plane. So inclined plane we'll discuss plane, okay, projectile motion in inclined plane, and projectile motion or when the projectiles are projected from certain height in the horizontal direction or in the oblique direction. So these are the main focus will be there in the next class. These are very, very important to solve various numerical problems. Okay, thank you very much for your patience. Bye for today.